but because r is a function of q, and q is a function of time, when I go to calculate r dot, then the chain rule shows up. Right? So the chain rule, it just says partial r partial q1 times q1 dot plus partial r partial q2 times q2 dot plus partial r partial q3 times q3 dot, because we have three parameters here. And this is in this chapter 5 as well, all of this description of Jacobian matrices, starting on page 117 and going all the way through there. I calculated them all for all these different parameterizations. The notation is a little bit different. In the book, I call this, instead of B, I call this R. And instead of S, I call this L for right and left, which is where the dot is. Here, our dot is on the right. Here, our dot is on the left. Okay? So, omega R in the book is the same as body fixed. Omega L in the book is the same as space fixed. Okay, so what we get, say for the body fixed version of angular velocity then, because of the chain rule here, what we get, and because this V operator that we've discussed before is linear, meaning that if I take constant C1 times one skew symmetric matrix plus constant C2 times another skew symmetric matrix, and I take the vector of that, that's the same as C1, the vector, well, I'll just write it out. Okay. If I take C1 times skew symmetric matrix 1 plus C2 times skew symmetric matrix 2, and I take the vector of that, that's the same as C1 times the vector of S1 plus C2 times the vector of S2. So, using this fact, together with the chain rule and the definition of angular velocity, we can write omega b, I'll write it over here. Omega b is equal to R transpose partial R partial Q1 V times Q1 dot plus R transpose partial R partial Q2 V times Q2 dot plus R transpose partial R partial Q3 times Q3 dot. And this whole thing can be written in a matrix form where I pull out the Q1 dot, Q2 dot, and Q3 dot and put them in a column vector, and I'll call that Q dot. And then the columns of this matrix over here are R transpose partial R partial Q1, R transpose partial R partial Q2, R transpose partial R partial Q3. And this matrix right here is called the Jacobian matrix, and this would be the body fixed Jacobian matrix, and it depends on Q. So it's a matrix, and inside of the matrix the elements depend on the Q, Q1, Q2, Q3, the parameters that are used to describe the rotation. So we have omega b is equal to JB of Q, this matrix, times Q dot. And an analogous expression holds for the case of space fixed rather than body fixed. So, so I'll write, who wants a break? 5-minute break? Or who wants to go straight through for another hour and 15 minutes? Break means you can disappear if you don't want to stay for the rest. Okay, let's take a vote. So, there's two choices. Break, no break. Raise your hand if you want to break. Okay, raise your hand if you don't want to break. Okay, most people don't seem to care. Maybe you're already on a mental break.
When you say hour and 15, you mean 45?
Oh, how long have I been going?
Since 4 o'clock.
Oh, okay, yeah, we have 45 minutes left. Okay, yeah, right, 45 minutes left. Just soldier on. Yeah, it's a little hot in here though. Maybe we need to open the door a little bit. Okay, so no break, right. See, I was having so much fun, I just thought it was an hour and 15 went by rather than an hour and 45. Okay, so we do the same for omega s. And what that gives us is that the space-fixed version of angular velocity can be written in a similar way, but the Jacobian matrix, now instead of having columns that look like this, it will have columns that have these in reverse order. So it's partial r, partial q1 times r transpose, partial r, partial q2 times r transpose, partial r, partial q3 times r transpose, times q dot, for exactly the same reasons, the chain rule, etc. And so now, so we can write this as omega s is equal to j space fixed of q times q dot. Okay? Now, jb and js are related to each other. Okay? So if you've calculated one, if you've gone through all the effort of calculating one of them, you can fairly easily calculate the other one. And this comes back to a trick that you proved in one of your homeworks, which has to do with conjugating a skew-symmetric matrix by a rotation matrix. If I give you that R is a rotation, and S is skew-symmetric, then you proved that RS, R transpose, the vector of this, is equal to R times the vector of the skew-symmetric matrix S. Okay? So we're going to use that. We can use that fact because this is a skew-symmetric matrix, and this skew-symmetric matrix is related to this skew-symmetric matrix in a very simple way. Partial R, partial Q sub I times R transpose, and R transpose partial R partial QI are related. So these two matrices, so they're both skew-symmetric, and you can get one from the other by, for instance, taking this one and multiplying it on the left by R and multiplying it on the right by R transpose, and then you're going to get this one. Okay? And so what that means is when we go to calculate Jacobian matrices, which have as their columns the vectors of these skew-symmetric matrices, since this is equal to this, if I take the vector of this, that's going to be equal to the vector of this. And then we can use this formula right here, because we have an R and an R transpose, and a skew-symmetric matrix in the middle. So this is going to be equal to R times R transpose partial R partial QI, the vector of this. So what that says is that we can take the column of the any column of the body fixed Jacobian matrix, and the corresponding column in the space fixed version of the Jacobian matrix is just going to be that pre-multiplied by R. So if I give you a matrix J, so J space fixed, and it has columns, so I'll just call this column J1, column J2, column J3. Or maybe I should J1, S, S, S. And I say that each of these J sub I S's is equal to R times J body fixed I. So the corresponding column is simply pre-multiplied by R. So if I write that out, that's equal to R J1B, R J2B, R J3B. That's exactly the same. I can take all of these R's and just pull them all the way out front. So I get R, J1B, J2B, J3B. So what that means is that the space-fixed and body-fixed Jacobians are related to each other simply as Js of Q is equal to R of Q times JB of Q. And if you want to go the other way, you just pre-multiply by R transpose. So Jacobians of parameterizations of rotations, whether it's body fixed or space fixed, can be related to each other simply by the rotation matrix that is describing the rotation. Okay? Now, okay, we're getting very close to the algorithm that is in the microsatellite reorientation paper, because now what I called R of alpha, beta, gamma, which was the forward followed by the reverse rotations, let's just abstract it a little bit and call it R of Q. So, okay, so in a sense, you could have some other design. It doesn't have to be those particular flippers. Maybe you have little arms that wiggle around, and you could parameterize rotations in any way you like by having those arms undergo some repeatable maneuver, and you could call that R of Q. So whatever your method for reorienting your satellite without thrusters, just by internal motions of the satellite, we can call that R of Q. And so the idea is that you have the satellite, and it's at one orientation, and you want it to change orientation. And at the end of that changed orientation procedure, you want the flippers to be back in their neutral zero angle. Okay? So initially the flippers are unflipped, and you want them to flip and unflip and then change the overall orientation, but then you want the flip, at the end of that procedure, you want the flippers to be back where they were when you started. Because then you can repeat this procedure. Instead of rotating like this, you may want to rotate like this the next time. And so you always want to start from the same flipper state. So the idea in the paper involves Jacobians of the same kind that we're just talking about over here. And the idea is, suppose, okay, so if you're at this orientation, let's say at r at time 0 is the identity, and r at time 1 we want to be the desired rotation. Okay? So we want to go from an orientation of I to an orientation of r desired. And so the question is, how do we figure out the Q that will get us there? And so one way to do this, especially if you have many, so if the flippers are very small, when you undergo a flipping maneuver, you can only really change by a very small amount. Then you have to undergo many flipping procedures to reorient the satellite. So the idea is, let's construct an artificial path in the space of rotations from the identity to our desired. And one way to construct such a path is to say, let's say r of t. So here this is imaginary time, or it's an artificial time. It's not like an imaginary number. I don't know whether that should be an A or an E. One is for imaginary numbers and one is like imaginary, right? So, we have r of t, which starts at I, and we're going to construct a path in the space of rotations that terminates at the desired rotation when r is equal to 1. And there's a way to do that using the exponential that we talked about. And we can write it like this. So what is the log of a rotation matrix? Well, if you believe me that it makes sense to talk about the exponential, it shouldn't bother you if I talk about the log. The log is the inverse of the exponential. So if I give you that r is equal to the exponential of a skew-symmetric matrix X, then X is equal to log of R. Okay? And there's an easy way to calculate the log of R, because we know, based on what we talked about earlier today, what the exponential of X looks like. This is the identity plus sine of the magnitude of X divided by the magnitude of X times X plus 1 minus cosine of the magnitude of X divided by the magnitude of X squared times X squared. So it turns out that you can get X by taking R minus R transpose and dividing by the sine of the angle. And the angle can be extracted from R based on the eigenvalue arguments that we talked about before. In other words, theta of R, the cosine of theta of R, so if you have cosine theta, negative sine theta, the eigenvalues of this are the same as the eigenvalues of any rotation matrix by an angle theta around any axis. This is for around the z-axis, but the eigenvalues will be the same around any axis. So if we take the trace, that's equal to 1 plus, so the trace is of a matrix, the sum of the diagonal elements, is invariant under similarity transformation, and the trace is the sum of the eigenvalues. So the eigenvalues are lambda 1, lambda 2, lambda 3, which is e to the I theta, e to the negative I theta. That gives exactly this, which is the same as this. And so we can go to our rotation matrix, and calculate the trace of the rotation matrix. So I give you a rotation matrix R, numerical values, and ask what is the angle of rotation for that rotation matrix. The simplest way to do it is you simply sum up the diagonal entries. That's the trace of R. That has to be equal to 2 times cosine of the angle of the rotation plus 1. And then you can, from here, solve for what theta is. Doing it, subtracting 1, dividing by 2, and taking inverse cosine. Okay? So, and then once we know what theta is, as a function of R, we can put it in here, and we can get x. So we have a way to extract x from R. In other words, we have a way of inverting this to find x given R. And the way we define the logarithm of a rotation matrix is exactly this procedure that I just said. We do the opposite of the exponential. Or if you don't like that, type log m in MATLAB, and it'll give you the log of the rotation matrix. Okay? So we have a way to calculate the log of this rotation matrix, which is a skew-symmetric matrix. Then when we multiply that by t, ranging from 0 to 1, what this will do is this will give us a sequence of rotation matrices that start at the identity when t is equal to 0, because e to the 0 is the identity matrix. And then, when we get to t equal 1, we have exponential of log of this is equal to this. So this generates a path in rotations connecting the identity to our desired rotation. Okay? And having a path is the starting point, okay, for Jacobian iterations. And so what I want to do now is go back and talk about the robot arm and robot arm inverse kinematics by Jacobian iterations. And then that same procedure will come back over here and apply to the satellite problem. Okay? So these two things are really the same. It's just that you have to know what it means to be a Jacobian matrix in the context of rotation matrices, which is what we were just talking about. In the context of the robot arm, so Jacobian iterations, or inverse Jacobian iteration. So remember, we have our robot arm, and I'll just talk about the two-link case for now, where this is L1, L2, this is theta 1, this angle is theta 2, this vector to the end here is the position vector x. This two-link manipulator is essentially the same thing as a double pendulum. And the so-called forward kinematics are, you have the thetas and you want to find out what x is. So this is L1 cosine theta 1 plus L2 sine of, still cosine theta 1 plus theta 2, L1 sine theta 1 plus L2 sine theta 1 plus theta 2. That's the forward kinematics. And the way that, the Jacobian, x dot is equal to the Jacobian, which is a function of theta, times theta dot. So just like we had in the rotation case, we had angular velocity, either space fixed or body fixed. Description was equal to the corresponding Jacobian times the rate of change of the parameter vector. We have a very similar expression here. This one is simpler because it's a two-dimensional case. and we've worked out this before, what the Jacobian matrix looks like. This is, the first column is partial x, partial theta 1, and the second column is partial x, partial theta 2. So this is a 2 by 2 matrix. And the way that Jacobian iterations work is to say, if I want to numerically perform inverse kinematics, let's say that I start out in with some initial theta 1 and theta 2, and so I know where the hand is at time equals 0. So at theta 1 of 0 and theta 2 of 0 are given, which means that I know x at time 0. Okay? But then let's say that I want to reach a different point. And so what I will do is I will generate an artificial path trajectory, a path, which is x of t equals x of 0 plus t times, now this is going to be x desired minus x at time 0. So it's very much like this right here, except no exponential and log. Okay, because I'm here in the Euclidean plane, I can define a straight line, and I can still stay in the plane, right? A line can be contained in the plane. If I'm talking about rotation matrices, if I take rotation matrix 1, like the identity matrix, and rotation matrix 2, the desired one, you can't just interpolate rotation matrices because the result will no longer be a rotation matrix, right? I can't add two rotation matrices and have it be a rotation matrix. Likewise, I can't linearly interpolate rotation matrices, but I can linearly interpolate vectors in the plane. That's why this expression is so much simpler than that one. But the idea is the same. We're constructing an x of t that start out at a known initial, in this case, known initial position, in this case, a known initial orientation. Then I have a desired position that I want to reach over here, and I'm giving myself 1 unit of time to reach there. That's what I'm doing over here also. And the way that the Jacobian iterations work then is to say, you have x dot, so here time is artificial time. This is not the real dynamics of the system. We're just saying t marches along from 0 to 1 along this trajectory, and by the time we hit 1, we're at the place, at the location that we want it to be. And this inverse Jacobian iterations is sort of like a magic procedure to bootstrap up from the information that you know to make the thetas evolve to be the thetas that will make the hand reach where you want it to reach. And so the procedure goes like this. So you have, well, what is x dot? Well, you have x of t, an analytical expression for x of t, so you can calculate x dot. Similarly, over here, you have r of t as an analytical expression, and so you could calculate from this r of t what the omega, either body fixed or space fixed, would need to be in order to follow this trajectory. So I'm going, back and forth between these two problems because the procedure is the same, this Jacobian iteration procedure. So you have x dot so x dot is very simple in this case. X dot is just x desired minus x 0, right? That's the time derivative of x in this case. And so we have x dot, and so we say, okay, x at time, so we can take this, and as long as this Jacobian matrix is invertible, we can say theta dot is equal to j of theta inverse times x dot. Over there we could do the same thing, except instead of x dots we'd have omegas, and instead of thetas we'd have the q's, the parameters that describe the rotations. And we know what x of 0 is, and we know what theta 1 and theta 2 are at time 0. So theta of 0 is known, x dot is known, so we can get theta at time delta t, an instant later in time, is theta at time 0 plus delta t times theta dot at time 0. And then we just iterate. Okay? So in other words, that's why it's Jacobian iterations. So we start out with knowing theta 0. We calculate theta dot at time 0 from this formula. We then take that theta dot at time 0, substitute in here. We update our theta. So now we know theta at time delta t. Then our delta t is like our new 0. So starting knowing this, then we calculate theta at 2 times delta t by doing the same procedure. So we update this value of theta, we recompute the Jacobian matrix at the new value of theta. Instead of theta at 0, it's now calculated at theta of delta t. We use our new x dot, which in this case is the same as the old x dot. This x dot is the same throughout the iterations. But the Jacobian matrix changes, and every time you change the Jacobian matrix, you have to recompute and take the inverse again. And then you just iterate. And so the first step looks like I went from here to here. I found my theta at time delta t. And that moved me this much along the trajectory. And now from here, I'm going to take another step, and that's going to give me my theta at 2 times delta t. And then I'm going to keep marching along until I reach the end there. Okay? Now, this works pretty well, except for 2 things. One thing, the arm can hit what's called a singularity. When the arm is completely outreached or completely folded back on itself, then the Jacobian matrix, the determinant, can become 0. And that's called a singularity. So if the Jacobian matrix is singular, meaning the determinant is 0, it's called a singularity. If we hit a singularity, you can't invert the matrix. Okay? Fortunately, there's something called a pseudo-inverse. Right? So a matrix that's invertible, you can invert. A matrix that's not invertible, you can cheat a little bit. Okay? Let's strike that from the film. We don't want the YouTube audience to hear the professor advocating cheating. So here is what I mean. If I give you a matrix M, and M times X is equal to B, then if the determinant of M is equal to 0, then M inverse does not exist. But I still may want to have an X. So what do? Well, I can't find a matrix to pre-multiply this by that will give me an exact X, but I can find one that will give me the least worst option. I'll put it that way. Not the best, least worst option, just the least bad option, okay? So what we can do is reformulate this and ask, how can X minimize a cost like mx minus b. Okay? Well, it turns out, and we may want to put some penalty like, and the magnitude of x has to be finite, something like that. So it turns out that if you ask the question in this way, where epsilon is sort of a fudge factor, a parameter that allows you some flexibility in how closely you satisfy the solution, then this gives us a pseudo-inverse, and the pseudo-inverse looks like x equals, and I'm probably going to get this wrong, but it's m transpose plus epsilon times the identity inverse, something like that. So times b. So in other words, this matrix right here can be used in place of m inverse to give an approximate x that satisfies the solution. Now,